So welcome back, everyone. Good morning, good afternoon, or good evening, and welcome to today's DevOps.com program, brought to you by Techstrong and Yugabyte. My name is Cody J. Brown. I'm the host of Techstrong Learning, and we have an exciting presentation ahead. First, I do need to cover just a couple of housekeeping notes. Today's session is being recorded, so if you miss any of our discussion, perhaps you'd like to rewatch or share with a friend, the on-demand recording will be made available shortly after we conclude our live session today. If you have any questions, we'd like you to send those in to us using the Q&A tab. You can find that Q&A tab on the right side of your screen, where you'll also find a few more options. The first option you'll see besides that Q&A tab is the chat tab, and we'd like you to reserve that for more general comments or maybe good tidbits you hear from today's program. I'd also like you to start warming that up for me right now by letting us know from where you're joining. Now, at the end of our program, we will be giving away 4 $25 Amazon gift cards, so do stick with us for the duration of our program to find out if you've won. And our topic today is evolution of transactional databases. I'm joined by Kannan Muthukkaruppan, president and co-founder of Yugabyte. Kannan, thank you so much for being here with me. Would you like to take it away?
Thank you, Cody, first of all, and the Techstrong team for hosting this event. My pleasure to meet everyone that's joining in today. So good afternoon, good evening, good morning, whatever be the case, based on your time zone. Thanks for joining. Again, I'm Kannan Muthukkaruppan, like Cody mentioned, and I'm here to talk about the journey of transactional databases, right? And why another database. So I'm co-founder at Yugabyte. So I hope to weave that story of transactional databases in with a little bit of the motivation behind, why we started. I, along with my co-founders, started Yugabyte DB, working on Yugabyte DB about 7 years back. So let's jump right in. All right. So let me advance. All right. I would first like to take you on a trip down memory lane. So bear with me here. We're going to go back to the 1960s for a little bit. And you could say that some of the early work on data management systems actually began at IBM, and this was back in 1960s. And the initial release of IMS, which is the information management system from IBM, happened in 1966. And back at that time, the popular data model was actually the hierarchical data model, and it was essentially kind of a tree-like way of organizing your data. You had items like colleges, and colleges had departments, departments had teachers, but essentially this simple tree-like capability allowed you to model only one-to-many relationships. And thereafter, this network model was extended, this hierarchical data model was extended to support even end-to-end relations. For example, a project could have many departments, a department could be part of multiple projects. So definitely a little bit more expressive in terms of your data modeling capabilities. But either way, one of the main challenges with sort of this hierarchical data model of the early data systems was fundamentally the fact that the on-disk or physical organization of data was very coupled with how the applications would express their need to query this data. And anytime the query patterns changed, then suddenly you had to reorganize all the data. It was like a non-trivial problem because you have your app logic too dependent on the way the physical data is organized in your system, right? And this is around when a very interesting development happened. So we're moving into the 1970s, and June of 1970 came out a paper called a relational model of data for large shared data banks. And this was again coming from IBM's research labs by a gentleman named Edgar F. Ted Cord, often called just Cord or Ted Cord. But fundamentally, what this paper talked about was, hey, it's a lot more flexible to model your database as a collection of relations, and each relation is simply a collection of tuples or rows, right? And for example, you have a relation called movies and actors and studios, and there are no pointers between these, kind of like in the previous hierarchical data models that we saw. But this is more logical, like a field, like say a studio ID is linked from the movies table to the studios table, more as a logical relationship. And he pointed out specifically this issue of the prior data models with access path dependence, that the fact that the application programs were too tightly coupled to the physical organization of data. And the whole idea behind the relational data model and the motivation was to really decouple this, so that every time your query pattern changed, your programs aren't like impaired and have to be rewritten to the new physical data layout, or there's a lot of pain point around changing that physical data layout. By the way, if you notice that the term data banks, back in the 1970s, I think that was the more common name for databases, and over time, data banks became more popularly called as databases. So just an interesting tidbit there. But let's keep moving. And maybe just a quick sound check, Cody. Is everybody okay in terms of the sound? I noticed a few comments.
I can hear you fine, Kannan.
All right, let's keep going. So, while this paper came out, IBM was actually still busy with their IMS 360 system based on the hierarchical data model. Although Cord and his colleague CJ Date, who's also a very famous database famous person in the field of databases, although they were convinced about the power of relational data models, and in fact they evangelized it quite a bit within IBM. But IBM itself was a little bit slow to commercially accept and adopt this idea, and they were still quite focused on the IMS 360 product, right? So maybe a quick question for the audience: which one was the first relational database in your mind? I'll maybe pause 30 seconds if somebody wants to, and hopefully there is no time lag, but would be curious to hear from the audience what the first relational database was. All right, somebody said Oracle, someone said INGRES. Very quite true. So it was in 19, and I'm going to reveal the answer in very quickly. But in 1973, this team from the University of California, Berkeley, right, and the picture you see out here is that of Michael Stonebreaker, who's generally considered the father of the INGRES database. And this was essentially a research team working at UC Berkeley, and INGRES stood for Interactive Graphics and Retrieval System. In fact, it was one of the very first systems to demonstrate that it was possible to build a practical implementation of the relational data model, not just practical, but an efficient one, right? And a number of ideas from INGRES are relevant even today in many of the relational databases that we see around, like whether it was the concept of B trees or implementing integrity constraints, or the concept of like views and using like the query rewrite approach to views. Many of those still are popular and exist in today's relational database management systems, right? And in fact, the INGRES paper essentially talked about the same data path and independence, like having independence from the application program to the physical structure, the access path independence, if you will. And this paper calls out essentially the same things that Cord's paper from the early 1970s reflected, but these were the first ones to sort of start actually working on building such a system. And in fact, what is interesting is while Cord's paper presented the query ability and all in a little bit more mathematical fashion, here in INGRES, you start to see the beginnings of actually a query language. It was called Quell, Quel. If you look at the syntax carefully, this syntax is saying, hey, give a 10% raise to employee Jones if he works on the first floor. And you see that this is not quite the SQL that a lot of you are familiar with. So think of it as a precursor to SQL. It still has a little bit of the same notions. It's a very declarative way of expressing the query. It's not procedural, but the syntax is slightly different than what today you see with SQL. But a lot of the beginnings happened in this product in INGRES. So around this time, interestingly, just about a year after, in 1974, IBM also started working on System R, which was IBM's attempt at this problem. So they started building a relational approach to database management almost 4 years after the Cord's paper on relational model came out. And here they actually introduced what today looks very similar to SQL, but at that time it was called SEQUEL, and it stood for Structured English Query Language, right? And so this now is starting to look very much like SQL. But here's the interesting part, and I'll read the underlined last sentence at the bottom. It says, we emphasize that System R is a vehicle for research in database architecture and is not planned as a product. So even 1974, they are starting to work on this, but it is still a research product from IBM's viewpoint. So INGRES is also sort of a university project, although it's making a lot of advancement. So if you ask the question, who really started taking the forefront in terms of building a commercial database, it was this team, and I'm sure people recognize this team. But I'll look for some messages on the chat to see. Anyone wants to say who this team is? Probably a little bit of delay on the. All right, yeah, that's right. So 1977, the 4 people you see are the co-founders of Oracle: Ed Oates, Bruce Scott, Bob Miner, and yes, the tall person on the right is Larry Ellison. I think if I'm not mistaken, Larry probably put about $10,000 of his own money to get Oracle started. At that time, its name was, I think, RSI. And they actually started building a commercial system that was compatible with the IBM System R specification. And the first release of this product happened in 1979, right? And initially it was built on mini computers. But by 1983, it was already rewritten to run on many more systems like IBM PCs, Macintosh, and mainframes. So let's keep going. So like I said, 1979 was the first commercial SQL-based RDBMS. And 1984, then they started doing things like for more transactional use cases, like and like adding multi-version concurrency control. And keep in mind, like only in 1988, row-level locking gets introduced. That means like in the first 10 years or so, like concurrent threads modifying the same table, all that, maybe it wasn't as common, but by 1988 they said, hey, we can't be doing table level locks or page level locks. We've got to get finer grained than that, right? So it starts to get to like row level locking around 1988. 1988 is when they added support for PL SQL. Initially it was just anonymous blocks, and then by 1992 stored procedures were implemented as well. So triggers, parallel execution, and all that. And I draw some of this timeline, and I conveniently stop at around 1994. But that's around the time. I mean, a little bit of a personal connect happens. I joined Oracle fresh out of grad school. I just completed my master's at Berkeley, and then I joined Oracle in 1994. And proud to say, or whatever, like I also had contributed from 1994, almost spent 13 years at Oracle in the database team, working on a variety of features, and definitely it's a place where I can say I learned a lot. So let's continue that, right? But by 1980s, while Oracle expands, it's not that the other players are sitting quiet. So a lot of alternative solutions also start to emerge, right? And 1983, almost like 13 years after Cord's paper, from IBM Research Labs, IBM itself puts out their first version of the relational database, and it's like DB2. And another company in the Bay Area, Silicon Valley, also 1987, Sybase, they build a relational database, and then many more start to emerge, right? 1989, the team that built INGRES redesigns and starts from scratch a new database, and this is another database you're very familiar with, and it's Postgres. but they took a lot of the learnings from INGRES and addressed a lot of the shortcomings, and started Postgres. And to this day, Postgres remains a very, very successful project. And 1989, Microsoft started work on SQL Server, and there's a little bit of a story that actually the first version of the SQL Server product was built on code that Microsoft, I believe, licensed from Sybase. So they share a lot of common roots. Of course, over the years, Microsoft went on to modify and adapt and change that code base significantly, as you can imagine. I mean, these products never sit quietly. There's so much feature set and capabilities that need to be added in this journey. And 1995 was the first release of MySQL. So hopefully that gives you some context. But while all this was happening, by 1986, Oracle really starts to dominate the relational database market, right? And some of it is, principles of things like why. If you ask the question like why, it was not just that Oracle built a good relational database, but they also paid attention to certain other details like compatibility, portability, and connectability. Compatibility meaning like they saw that IBM had already published work on the SQL language, the system R, and so on. So rather than Oracle try to create a very different dialect, they largely stuck to being compatible with system R from IBM. Oracle was also one of the forerunners in terms of portability. Like back in the day, the number of operating systems and successful platforms, whether it was DEC, Solaris, HP, you name it, right? And Oracle was one that worked identically no matter which platform you ran on. And also connectability, like being able to connect from different machines on a shared database infrastructure. They paid attention to these details, right? And to some extent, these things are playing back again today in today's era, whether it is like you're building a database that can run on any cloud. Portability is still important. Your database working on ARM-based processor, like for example, AWS Cloud has Graviton machines, which are essentially ARM-based machines, or Intel. So that continues to remain important, right? And as a database company, we like behind Yugabyte also pay attention to these things, like not coming up with new APIs that introduce developer friction, or a database that only runs on certain hardware and not on others. So those continue to remain very important. All right, so let's talk about a few other trends that are sort of start to happen around this time, right? And we'll talk about single instance to going distributed. But before that, let me just make sure. Let me look at the Q&A channel as well in case there are some questions that I want to take at this time. All right, I think we're good for now. Let's keep going. All right. So by and large, the databases, in the 90s up to the 90s, mostly were single node systems, whether you think about Oracle or Postgres or SQL Server, MySQL. So as the applications needed more and more scale for their, from their database tier, what were some of the trends that started to happen? On the one hand, a company like Oracle built Oracle RAC, right? RAC was what Oracle called Real Application Clusters. This was in 2001. But keep in mind that Oracle's RAC solution requires pretty custom setup. Like for example, you need InfiniBand and fast interconnect, and it's still based on a shared disk architecture. So it had it is scalable, but not infinitely, and it requires it's not something that works well on a shared nothing commodity architecture. So a few other trends emerged. There was sort of like the wave of NoSQL movement also happened in the late 2000s, maybe like 2008-9 timeframe. But in this journey, I view like two forks in the road, right? On the one hand, there was a group of developers that went to NoSQL because of a data model preference. So yes, relational data model was very popular, but there was a large camp of people that also liked a document data model, right? And this group was largely served by databases like MongoDB, Couchbase, where essentially it was a very document-first way of data modeling, right? kind of like schema-less. You could put any JSON document in your collection, and a lot of the schema enforcement was, it was both easy to get data in, but it had its challenges if you then later wanted to tightly restrict the schema. But nevertheless, this was quite a popular NoSQL movement. But there was another kind of movement towards NoSQL because of applications needing a very large scale, and distribution and built-in replication of data across multiple geographies and so on. So essentially, this was, I would say, the cloud-native applications demanding more throughput, more scale, more resiliency, and active availability across even node failures and zone failures. Because fundamentally, the cloud was built of commodity hardware, commodity building blocks, and the promise of the cloud was the scale as you go, right? And rather than upfront buy a large giant machine to run your database. So when databases had to be evolved to address this large scale, distributed kind of scale, essentially it was a hard enough problem, both dealing with sharding, replication, load balancing, all of that on commodity hardware, and also supporting the full breadth of relational database functionality, that this camp said, for the first wave, let's not worry about giving the full power of SQL and the relational database, foreign keys, referential integrity, all that. Let's constrain the problem. Let's keep the API to the database pretty simple. Let's keep it kind of like a key value abstraction, but let's focus on providing that massive scale and linear scalability. So a whole bunch of NoSQL databases evolved, including Google's Bigtable, DynamoDB, and that combination of Google's Bigtable and Amazon's Dynamo, served as sort of the parent NoSQL databases to a whole bunch of other scalable systems like Cassandra, HBase, Azure Cosmos DB, and so on. And in fact, me and my co-founders, we were involved with some of these systems, especially Cassandra and HBase, during our tenure at Facebook, and I'll go into that a little bit during this talk, right? So let us look at some of the data architecture at these internet scale companies in the 2010s. By the way, so we'll start a little bit with Facebook, because me and my co-founders met at Facebook during this period somewhere back then, right? And up until 2007, Facebook's data architecture was largely running on MySQL. Obviously, not one MySQL instance, but I would say thousands of MySQL instances. So it was sharded at the application layer, and the application tier roughly dealt with two key infrastructure components. One was MySQL, which is where the source of truth of the data was, hundreds of MySQL instances. But because we were constantly worried about bottlenecking MySQL, and especially whenever you add a new feature, you worry about can the system handle more? Can it handle a read spike and so on? So very quickly, Memcached was added in as sort of a caching tier, right? But now it was the application's responsibility to cache what it needed in the Memcached caching tier, and also keep these two tiers consistent. Whenever MySQL data in MySQL changed, the application code now had to invalidate the contents in Memcached and kind of keep it consistent. So it was, as you can imagine, this is getting hard enough in a single data center type of environment. But you can imagine now if you had multiple data centers from which you're serving traffic, and you're doing MySQL replication at the database layer, and you have Memcached also in many, many data centers, very quickly this whole thing gets pretty complicated, right? So what did Facebook try to do? It tried to hide a lot of this complexity away from the application tier. It said, hey, the application tier can no longer use SQL to communicate with the data tier. We'll build an abstraction. That abstraction, the data access layer, was called TAO, the Objects and Association Service. And all of the Facebook's application code had to use the TAO API. And now it was all the logic of keeping the memcached and the MySQL systems consistent and across data centers was now suddenly the responsibility of the Tau framework. But at least the good part was most of the application developers didn't have to worry about the cache and the MySQL, right? And so essentially by restricting this API, Facebook made this solution a lot more scalable within its organization. But however, as you can imagine, this solution is very Facebook private, right? It's hard to take it to a larger market, right? It's hard to take it to a larger market where they can live with the restrictions of this API. Like it's no longer SQL. It doesn't have all the, you want to create an index, you want to add a foreign key, none of that, right? You're constrained by this. So this worked for Facebook's own use, but it is not something that you could think of as a general purpose database. So even with all that work, some applications were growing so fast, right, that constantly adding more MySQL shards and rebalancing the data between these shards was getting out of hand. So this is where Facebook started investing in NoSQL databases, and we did a lot of work for some applications like Facebook Messenger that were so fast growing, like getting to almost 20 billion messages a day on Facebook Messenger, and petabyte scale of data on these systems, that we decided that the database itself should handle that elasticity, like ability to just add nodes into your cluster, and it just rebalances and automatically shards, automatically replicates between data centers. And like I said, the first wave of these distributed databases were NoSQL, and me and my co-founders worked on projects like Cassandra and HBase, and helped put these systems in production at Facebook. And right here, I would like to just kind of take a context switch into things that people love about SQL and things that people wish SQL had, right? So because sort of this fork is happening all the way to NoSQL databases and different data models and so on. So firstly, it's worth recapping that why developers love SQL, right? It has a super rich data model and query flexibility, because you can easily add an index, and the queries are very declarative. You can join between tables, very rich data model, right? Support for transactions. I can move $10 from one account to another account in an atomic transaction. I mean, relational databases have done this for 30-40 years, but a lot of NoSQL databases don't have multi-row transactions or multi-shard transactions, which means the app developer has to deal with a lot of that logic in a NoSQL database. So that's really the power of SQL. Of course, not to mention the rich ecosystem that's already around, the number of developers and the familiarity in many organizations for building applications to a SQL API. So those are really some of the strengths of SQL. But some of the reasons developers had to struggle with relational databases and were forced to go to NoSQL was mainly some of these that we list here. One is the fact that most relational databases were single node databases, not really scalable. And so if you needed scale, you were forced to go to NoSQL and give up on a lot of the flexibility of SQL. Also, a lot of the single node databases, the failover support, whether you have active passive or active, a lot of those, the high availability of the system was an afterthought, right? Whether you think of building your resilience for your Oracle database across data centers by adding a Golden Gate replication, any of those, right, are built as an add-on. Whereas I think one of the nice things about NoSQL is that all of that is built into the database. But ideally, you would like to have the best of the two worlds, right? Especially when you want to also then distribute your data across multiple geographies and have a variety of deployment flexibility in terms of, do I have synchronous replication between data centers, asynchronous replication between data centers? So it would be great to have a database that kind of brings the cloud native properties of NoSQL databases, but keeps the development flexibility and data model richness that comes with relational databases. So in some sense, that was our inspiration also to build Yugabyte DB. But let's keep following the course of evolution of the transactional databases. We looked at what Facebook and Facebook's engineering teams did with Tau and NoSQL. Some of the reasons for going with the Tau approach was Facebook had done a lot of investments in MySQL, and they wanted to preserve those investments while still helping the applications adopt and build a very scalable data infrastructure. But not all engineering teams came to the same conclusion. Any guesses on what database powers Google AdWords and Google Play? I'll wait 30 seconds to see your answers. Yeah, that's right. It is Spanner. So what is Google Spanner, right? In 2012, a paper came out, and it is a SQL database that can scale horizontally, right? So Bigtable, somebody responded Bigtable. Yes, Bigtable was kind of a precursor. It was a very distributed database at Google, but it was a NoSQL database. And at some point, SQL, like Google ads, products, and so on, moved to Google Spanner. And I've underlined a few important lines from the Google paper. So as part of rewriting Google's advertising backend, one of the things they said was resharding this revenue critical database as it grew in the number of customers and their data was extremely costly. The last time they had to reshard meaning, let's say it was sharded across 32 MySQL instances, and they wanted to reshard it to 64 MySQL instances. The last resharding took them over 2 years of intense effort and involved coordination and testing across dozens of teams to minimize risk. So same kind of challenges. They wanted to avoid this resharding of MySQL, but rather than continue with the NoSQL approach, at some point, Google said, hey, let's try to build a relational database that can scale, right? So Google Spanner is horizontally scalable, globally consistent, and it's a relational database that supports SQL. However, we'll see that there are kind of a little bit of differences between Google's approach to building the SQL layer versus Yugabyte's. But nevertheless, the point that just because you want scale and elasticity, you no longer have to give up on transactions, SQL, query flexibility. That sort of came through from the Spanner paper, right? So this definitely, you could say, was the beginning of the distributed SQL category, right? In terms of transactional databases, the distributed SQL movement, we could say that was born with the Google Spanner project. So in a nutshell, distributed SQL lets you keep the things you like about SQL and remove some of the things that you didn't like about SQL databases by giving you rich SQL features, horizontal scalability for your reads and writes. Writes are the harder one, right? Fault tolerance with very high availability, globally consistent writes, and very low read latencies, right? So, all right. But let's look at what some of the other cloud providers were also doing at this time. So while Google built Spanner, another very popular product came from Amazon's cloud services team, AWS, right? Which was Aurora. Aurora was launched in 2 form factors. One was a MySQL form factor, a fully managed service deployment in the MySQL form factor. That was in 2014. And about 3 years afterwards, in 2017, Aurora launched the Postgres variant of their service. However, it's worth calling out that it is not truly a distributed SQL database. The storage layer, the things that you see in the gray box on this picture are indeed distributed within a single region, right? It's a single region multi-zone type of storage layer. However, the database node marked as M here, the primary, is actually a single node. So all the query processing in Aurora goes through the single node, right? and the R's are read replicas, so they are kind of like hot standbys. They can serve reads there, but they're kind of serving potentially a slightly stale version of the data. So if you want strongly consistent reads, you're down to the single node database, and only the storage is distributed. It is worth calling out that in 2019, AWS Aurora did add some multi-master support, but if you read behind the lines, this has a large asterisk. There's still a lot of restrictions. It's still a single region. Multi-master is not truly scalable to many nodes. I believe the restriction is somewhere like 4 nodes, and it has a lot of other caveats of things that no longer work if you're running the system in multi-master mode. So it's something that may be a good candidate for certain restricted use cases, but it's not truly a distributed SQL database. All right, so there we can kind of now context switch a little bit into sort of the Yugabyte journey, because now the timelines are converging. So around 2016, and by this time we had spent about 6-7 years at Facebook, and my two co-founders and I started this in Yugabyte. Started Yugabyte in 2016, and I'd like to take you through a few of the key technical decisions and moments in Yugabyte history. I'll just start with this one. That's me on the far right, but it's from left to right. It's Mikhail and Karthik, my two other co-founders. And around Jan 2017. So we just came up on 7 years at Yugabyte, and thanks to all of many of you that have played a part in this journey, whether trying our open source database, giving feedback, or as users and customers of the product. We appreciate you coming in that journey with us. And but to set the stage a little bit, what was our motivation, and what are some of our key design goals, right? So, like I said, we wanted to bring the best of the SQL and NoSQL databases in a single product, and we believed that, like, by a lot of the NoSQL databases didn't support transactions, or even for single row they were eventually consistent. We firmly believed that was going to be hard for a large class of OLTP applications to be able to adopt. So strong transactional consistency, building the system in C++ for high performance, having a very layered architectures that today we already support 2 query layers. One is a Cassandra compatible interface, which is YCQL, and another is a fully Postgres compatible interface called YSQL. But both these query layers sit on this layered architecture on top of the DocDB storage layer, and this architecture is pretty extensible in future if we decide to support other APIs, right? And last but not the least, a few things about like really being cloud native, meaning run in any cloud, run on any infrastructure, whether it is on bare metal or VMs, right? And truly, address high uptime as a first principle, like whether you're updating a configuration flag or updating the version of Yugabyte DB from, say, release 2.12 to 2.14, or just adding nodes to the cluster. These should be really online operations that you don't really need to take a downtime for, right? So these were some of the guiding design goals. And it was not just us in 2016 that felt that building a transactional scalable database was important, right? Because remember, Google Spanner was actually an internal product till then. Only in 2017, Google launched Spanner as an offering that end users could also use. In 2018, MongoDB added support for multi-document transactions. And 2018, DynamoDB, often people say Dynamo really like push the concept of like eventual consistency is good enough for a lot of use cases. So even Dynamo add support for transactions in 2018, right? So this we are not alone. That this is a commonly recognized thing by the late 2010s, that transactions are important in a scalable system. A few other notes, like when you're building a system like this, essentially we're building something like Google Spanner as a small startup, small team. From very early on, we put immense emphasis on testing automation, right? And our team, even by the end of 2016, was probably just about 10 or 12 people. And one of my co-founders, so Mikhail, really put emphasis on this test automation. What you see here is a screenshot of when a developer in Yugabyte submits a pull request for review. Most of the time, by the time the reviewer has gotten to the pull request, a whole bunch of automated tests have already run. And not only that, because this is code based in C++, it is important to test the code in many, many different modes under many compilers, so we test with CLang, with GCC, with address sanitizer turned on, thread sanitizer turned on, things that can catch like very interesting race conditions and so on, like with Intel processor, ARM-based processor, and so on. So by the time a reviewer starts to review even the pull request, a lot of that tests have already completed. This was an important early emphasis. Another thing that we emphasized was, in addition to building the database itself, in 2016 we started building a very cloud-native control plane. Like this is like consuming the database as a service, right? And and we provide options of whether the database and the control plane run in our users VPC, or does Yugabyte fully run and manage it for them. Either way, the notion of, say, suppose you're in Google Cloud and you want to create a 30 node cluster in a particular Google geography with, say, N1 standard 16 machine type. This control plane makes all that trivial, right? Like it's not only programmable through a REST API, but it has a nice UI where I can just go in and in a matter of minutes, satisfy this request by clicking a few choices. So these were things that we started building early on, in addition to building the database itself. But as you can imagine, it takes time. This is a picture of the team around 2017, still a small team. It's probably the entire team back then. Maybe we're missing 3-4 people in this picture. But by 2017, we still don't have the product, right? We're still building it. And in 2018 May is when we actually announced the first release of the product. And obviously a journey like this, we try to kind of share a little bit of under the hood on how we decompose this problem into bite-sized chunks. Right? Initially, we built the storage and transaction layer. The first API was our Cassandra compatible API, YCQL, and by 1.0, our SQL API was still in very early beta. It wasn't quite ready, right? And so we had the Cassandra compatible API, and our PostgreSQL based API was in early beta. So this was May 2018. And just a little bit, like I won't spend too much time on this, but we picked PostgreSQL as the API for our SQL offering. Because it just has a very solid ecosystem. The open source license and DNA is very strong community, but just a very extensible and powerful feature set from early days. And a small backstory here, which I didn't mention earlier. 1992 to 94, I was a grad student at Berkeley when Michael Stonebreaker was still there. This was before he moved to East Coast. And my graduate level database course I took from Michael Stonebreaker, and all of us students as part of that course had to do a small project on Postgres, and Postgres was an extensible database, and I believe we had to add support for a polygon data type as an extensible type to Postgres. So that was our course project. Fun project. Little did I know that almost 25-30 years back, a lot of we'll go back to Postgres code, and Yugabyte actually uses a fair bit of Postgres code, and we'll cover that in the next few slides. But I thought I would mention that aspect. I just think it's really cool that, and it was not planned. It happened this way almost 25 years after my grad school work. But what are some of the goals we set out for our SQL offering, right? Like you could say Spanner is a dialect of SQL, right? But they have, I would say, slightly different goals. They support a small subset of SQL. Now they're trying to add Postgres functionality. But for us, from very early on, we said that, hey, we are not a SQL database just because we support these 4 or 5 commands like select, update, insert, create. We really want to take that notion all the way, right? And like we wanted to support like all the bells and whistles of like data types, queries, built-in functions. If Postgres has like a random number generation utility or a crypto UUID generated utility, we want to support as much of that out of the box. Triggers, stored procedures, right? Partial indexes, expression-based indexes. We wanted to remove the surprises when people are trying to modernize their application to a cloud native, scalable infrastructure stack. So that was a key goal. So the very next question was, how do we get to that goal? Do we build this from scratch, or do we try to reuse as much of Postgres code as possible? And both approaches, believe me, have their pros and cons. So we said, hey, like PostgreSQL code base is complex. It's like 30, 40 years old. Can we really go into such a code base, almost remove half of the lower half of it, and make it distributed and all that, right? Like, so it seemed like that would be risky, right? Like trying to reuse the code base and getting engineers excited about dealing with an existing code base, right? But as we looked into the problem further, we said like, okay, if we want to fit into the Postgres ecosystem, like we would like the command line utilities, like say Postgres' CLI, PSQL to work out of the box. So if you go into PSQL and hit /d to describe your schema or tables and things like that, internally, how does that query look like? Behind the scenes, this is what gets generated and sent to the Postgres server side, right? You can very quickly see that there is use of the Postgres system catalog tables, and there's like joins, left join going on, and functions like is Postgres table visible, all kinds of stuff happening even for just doing /d. So very quickly we realized that we will actually reuse the PostgreSQL's query layer, the upper half code at least, right? And doing so has allowed us to do something that many other distributed SQL databases do not do, right? They don't support most of the features that we saw in the last few slides, right? So building these features from ground up is going to be hard and takes a lot of time. And so very quickly, and this is a little bit, I'll just pause here. So this is so after making so we had actually well, initially we had actually started down the path of building our own implementation from scratch, but then we started a parallel effort, and in about 3 to 4 months, the very beginning, like you say, proof of life of the new approach started to emerge. This particular shot is in our office, and you're not going to be able to hear the video that much. But when the very first create table and insert and select started working, right, we huddled around one of the engineers' desk, and I'm recording this camera, and just our excitement when the first basic thing started working. It's a short 10-second clip. You won't really hear the audio, but let me play it for a little bit. Yeah. So my two co-founders, Karthik and Mikhail, are also in that clip. Let me keep going. All right. Yeah. All right. So essentially, and then obviously, it takes a while from the very first proof of life demo running on a developer's personal workstation or dev server to actually committing code and getting it into things that other people can try. So by 2019 March, we had kind of pulled it off, and it's worth calling out that it's not just that there's the Postgres code is running in a single node and it's running on top of our distributed storage layer. Every node, so the right-hand side of this picture, what you're seeing is every node in a Yugabyte cluster has the Postgres query layer as well as the storage engine, right? So it's truly a distributed architecture. Any node can receive requests, handle requests, coordinate transactions, and so on. So there's a whole there's probably a whole topic in itself, like how Yugabyte's distributed architecture works, but that's beyond the scope of this talk. And another decision was, whether to open source or not, and so on. And But long story short, the Yugabyte database is fully open source, meaning there isn't an enterprise version of the Yugabyte DB and an open source version. A feature like backup, encryption on the wire, encryption at rest, they are all available in Yugabyte's Yugabyte DB as Apache licensed project. So the entire database is open source. And one of the columnists and developer advocates who was at Adobe at that time, Matt Essay, I believe he's at MongoDB right now, and he had this to say about that by making the database 100% open source, Yugabyte DB removes other roadblocks to adoption. We do believe firmly that open source is a great way to build developer trust and a strong community, and we're very happy with that decision of going 100% open source. But like with transactional databases, the journey is still on, as in you are trying to build functionality that has been common for 30-40 years in relational databases, right? So here's just a snapshot of a little bit of how, when some of the features got added. The very early versions of Yugabyte, the database was working, but we didn't have backup restore functionality, for example, right? Like being able to back up your database and restore it back. And even if you just take backup restore as a area, initially our backups were only single shard consistent. So then we added support for multi-shard atomic backups. And then another evolution in that journey was adding features like point-in-time restore. Maybe I have an 8 p.m. backup and an 8 a.m. backup, but how do I get back to a state of the world as of, like, say, 7:55 a.m., right? So those are all features that, as you can imagine, you cannot build all at one shot, and we'd have to layer things in. So generalized inverted index, or GIN indexes, is something we added in 2021. One of the things that we're quite excited about is the Yugabyte DB Voyager that whose 1.0 version was announced just earlier this month. It's also an open source project, and it is a utility or tool that helps you deal with the entire life cycle of data migrations. And this is a tool that helps users come off of other databases, traditional databases, to Yugabyte. So it's a tool focused on the data migration journey. We call it Voyager. But lots of interesting things, like we added support for save points last year. Things like online index rebuilds, like you have a table with terabytes of data, you want to be able to add a new index, right? And this was not something we had in 2019, but around 2020 we added support for that. So it's a fun journey, and we hope to continue with momentum like before, and appreciate all the people, the early adopters, and if you have questions, you can always join us on our Slack channel, yugabyte.com/Slack. And I think that was my last slide. Thank you, everybody, for listening in. Maybe if there are questions, I'll take a look.
So, Kannan, while we wait for a couple of questions, I do just want to give away some gift cards.
Yeah.
So our 4 winners of our $425 Amazon gift card drawing are Janardhan K, David S, Tat L, and Louise F. So to our 4 winners, congratulations. Keep an eye on your inbox to claim your gift card, but if you don't happen to see that email in about the next 48 hours, do check your spam folder. Now, also take this opportunity to remind everyone that this session was recorded. You will be receiving an email with a link to access this recording on demand, or of course, you can find it living on the DevOps website at devops.com/webinars, and just be sure to look in the on-demand section. All right, Kannan, did you happen to see any questions come through?
Yeah, there was one question about, like, Postgres is known for many security issues. How do you assure that Yugabyte DB is secure? I mean, like with anything, it's a combination approach to tackle this. Of course, we reuse about half the Postgres code base, and we keep an eye on security issues that we either need to pull into our code base, fix, and responding promptly to those issues. But at the same time, the product itself is put through a lot of security tests, InfoSec compliance, code auditing, tools like Snyk. I don't remember exactly the tools we use, but that is a big area of focus, as you can imagine, for us as a company, and that's what our customers and users would like us to be focused on as well. And then the product itself, whether it is features like on-disk encryption, on-the-wire encryption, rotation of keys in an online and safe manner. Those are all a lot of features built in that are security focused. Even a recent capability we added, for example, is like people wanted ability to kind of lock out a user if they have more than n failed login attempts. So just like your phone, if you have n logged in n number of failed attempts, you get logged out and things like that. So a lot of those features we continue to build into the product. Another question is, can Oracle DB be migrated to Yugabyte DB? Certainly, like in terms of in the tool that we talked about, Yugabyte DB Voyager, it's really designed for that type of activity, right? And the entire life cycle from the preparatory step to schema migration to the actual data migration. And the initial version of it is mostly for offline migrations, but then we are also working for capabilities to do more online live migrations from one system to another. Can we use screenshots from the presentation in order to post on LinkedIn? Yes, that should be fine, totally fine. There's another question about when will the hyperscalers make a product of your investment? Yeah, that's something we'll watch out for, and I think we are hoping that hyperscalers won't try to fork our product and create their own dialects, because at the end of the day, it is the end user that will be unhappy if every hyperscaler ends up with their own dialect of SQL and a distributed SQL database. So and we are seeing interest in more partnership approach from hyperscalers. So that's exciting.
All right, Kannan, is that just about every question that we're seeing?
Yeah, we covered it, Cody.
Perfect. Well, I do want to give you the opportunity to leave our audience with any closing remarks or anything that you feel they absolutely need to take away from today.
Yeah, thanks, Cody. Again, I wanted to thank everybody that joined this session. Thanks for the questions. It was a pleasure to talk to you, and I hope you found it useful as well. And if there's anything, check us out on yugabyte.com or our Slack channel. So thank you very much. Have a great day and rest of the week.
Great, you too, and thank you so much, Kannan. I really appreciate the time that it takes to put together the presentation and the time out of your schedule to come out and present in front of everyone today. So again, thank you so much.
Awesome, thank you.
I'd like to also thank Yugabyte for sponsoring our program today, and to everyone who's been with us in attendance, thank you so much for being with us live. We really appreciate your time, and we also really appreciate your feedback. So as soon as we close out, there will be a survey that pops up on your screen. We'd really like to hear from you. Let us know what you thought about our program, or maybe what you'd like to see on an upcoming program. But otherwise, we do hope to see everyone at a future Techstrong learning experience. Have a great rest of your day. And again, Kannan, thank you so much.
Thank you. Thanks, Cody. Bye.